Real-world applications of machine learning. Introduction. Machine learning isn't just something that lives in research papers and Kaggle competitions. Right now, it's reading X-rays before doctors even look at them. It's steering cars through rain at night. It's writing the text you're about to read on your phone. And it's the reason your streaming service somehow always knows what you want to watch next. In this video, we're going to leave the theory behind and look at where machine learning actually earns its keep in the real world. We'll cover 4 huge domains: healthcare, natural language processing, autonomous vehicles, and recommender systems. For each one, we'll look at what's working, how it works conceptually, and, just as important, where it still breaks down. By the end, you'll understand not just what ML can do today, but why some of the hardest problems in these fields are still wide open. Let's get into it. ML in healthcare. Healthcare generates an enormous amount of data: medical images, lab results, electronic health records. And all of that data needs to be interpreted, often under time pressure. That combination is exactly what makes healthcare such fertile ground for machine learning. The area getting the most attention right now is early disease detection, especially in medical imaging. Convolutional neural networks, CNNs, have been trained to automatically segment cartilage in knee MRIs to assess osteoarthritis risk, and they outperform manual, non-ML approaches at this task. Deep learning models have also been used to segment multiple sclerosis lesions in 3D MRI scans, and to tell the difference between benign and malignant breast nodules on ultrasound images. One of the more striking results: CNNs, trained on roughly 130,000 clinical images, matched the diagnostic performance of actual dermatologists when classifying different types of skin cancer, including keratinocyte carcinomas and malignant melanomas. That's not a small proof of concept. That's models performing at a specialist level, on a task where catching something early can be the difference between a minor procedure and a life-threatening diagnosis. But imaging is only half the story. The other major front is electronic health records, or EHRs. Here, the goal shifts from what's in this scan to what's likely to happen to this patient. CNNs have been used to predict conditions like congestive heart failure and chronic obstructive pulmonary disease directly from a patient's clinical history, and they've shown real advantages over simpler baseline methods. Recurrent neural networks, RNNs, bring a different strength to this problem. They're built to handle sequences, which makes them a natural fit for a patient's history unfolding over time. RNNs have been applied to word embeddings of clinical notes to infer a patient's current illness state and predict future outcomes, and separately to predict future diagnoses and medications based on a patient's history, with meaningfully higher recall than non-deep learning baselines. Deep learning has even been used to model continuous signals, like a stream of lab results over time, to automatically identify patient phenotypes. Language models, the same broad family we'll talk about in the NLP chapter, have also been trained on EHR text to learn embedded representations of medical concepts. That's enabled applications like predicting suicide risk from clinical notes and automatically de-identifying sensitive patient records. And one particularly practical use case: predicting unplanned hospital readmissions. One study showed CNNs could accurately predict a readmission within 6 months of discharge, which matters enormously because early intervention can often prevent that readmission from happening at all. So, with all of that promise, why isn't ML running every hospital's diagnostic pipeline already? 2 words: trust and accuracy. Medical AI still makes mistakes, And in this domain, a mistake isn't a mislabeled photo, it's a missed or incorrect diagnosis. Part of the problem is data volume. Compared to, say, the internet-scale text and image datasets that power other ML applications, medical data is scarce. And what exists is often messy, heterogeneous formats, inconsistent timing, high complexity. Many current models also assume static inputs, which doesn't reflect how diseases actually evolve over time in a real patient. There's also the interpretability problem. A model that says, "This is cancer," without being able to explain why, is a hard sell to a doctor whose license and whose patient's life is on the line. Looking forward, the field is pushing toward federated learning, which lets models train across multiple hospitals without the raw patient data ever leaving each institution, plus differential privacy techniques to protect individual patients, even as models learn from aggregated data. Combine that with better temporal modeling and genuinely interpretable architectures, and healthcare ML starts to look less like a black box and more like a trustworthy diagnostic partner. Natural language processing. Natural language processing, NLP, is the branch of machine learning focused on getting computers to actually understand human language, whether it's spoken or written. If you've ever used a voice assistant on your phone or talked to a large language model like ChatGPT, you've used NLP. Almost all modern NLP is built on a single architectural family, transformers. Like CNNs and RNNs, transformers are a class of neural network, but they're specifically designed to handle sequences of text by learning which words in a sentence should pay attention to which other words, regardless of how far apart they are. That attention mechanism is what lets transformers capture long-range context in a way older architectures struggled with. The most talked about application of transformers right now is the Generative Pre-trained Transformer, GPT. These models learn from massive volumes of text and then generate original responses to prompts. OpenAI's ChatGPT is the most well-known example, and at its core, it's trained using the exact same ML pipeline we'd use for any other model. Collect data, choose an architecture, train, evaluate, refine. It's worth pointing out, and this is almost a little meta, that when GPT 3.5 was asked to explain how it works, it described its own training process in terms that map directly onto the ML pipeline. Pre-training on a broad slice of internet text to predict what word comes next, a transformer-based architecture that uses attention to process sequences, the option to fine-tune the general model for specific tasks, and a resulting ability to do things like answer questions, generate text, and translate languages. While being upfront about its own limitations, like occasionally generating incorrect or nonsensical output, being sensitive to how a prompt is phrased, and having no real understanding of context, personal experience, or emotion. That's a useful reminder. No matter how fluent or capable a language model seems, underneath it's still the same fundamental pipeline. Data in, patterns learned, predictions out. The scale is what's changed, not the core idea. Autonomous vehicles. When most people hear autonomous vehicles, they think of self-driving cars, but that's really just the most visible piece of a much bigger picture. ML is also driving autonomy in unmanned aerial systems, drones, autonomous maritime vessels, and delivery robots. In every case, the core challenge is the same: perceive the environment, make a decision, and navigate, often in real time, often with lives or expensive equipment on the line. Self-driving cars are the flagship application. These vehicles are loaded with cameras, LiDAR, and other sensors, and deep learning models process that sensor data continuously as the car moves. Most of these models are trained offline first, using a huge mix of real-world and simulated driving data. But training doesn't necessarily stop once the car is on the road. Some systems continue learning during deployment, with updates either staying local to a single vehicle or getting rolled out across an entire fleet through a software update. Drones, or UAS, unmanned aerial systems, are a fast-growing use case, especially for obstacle avoidance, navigation, and route planning. In agriculture specifically, drones equipped with ML can fly over farmland, photograph crops, and process those images on the spot to assess crop health, spot pests, and optimize irrigation, sending results straight to farm personnel without needing to offload data to a remote server first. The underlying ML approach is essentially the same as for self-driving cars: train offline, then deploy for real-time, on-device processing. Autonomous ships and underwater vehicles follow a similar pattern, using sonar and radar instead of cameras and LiDAR, with deep learning handling navigation, collision avoidance, and path planning through the added complexity of maritime environments. It's a newer, less mature application area, but one with both civilian and military potential. So what's holding widespread deployment back? Two big problems. First, representativeness of training data. Imagine training a model to help ships avoid collisions using images collected only on clear days. That model is going to fail badly at night or in snow, and because vessels are only realistically in motion under a limited range of conditions, building a truly representative dataset is genuinely hard. Second, there's a security problem. Transmitting live sensor data from a fleet of vehicles back to a central server can be risky, especially for navigation-sensitive applications. One proposed solution to that second problem is federated learning, the same technique we mentioned in the healthcare chapter. Instead of transmitting raw data, only model parameters get sent, which keeps the underlying data local and private. It's a promising direction, but it isn't a silver bullet. Federated learning is still vulnerable to attacks where those transmitted parameters get intercepted and reverse-engineered to reconstruct the original training data. Making autonomous vehicle ML both representative and secure is an active area of ongoing research. Recommender systems. Every time you get a "you might also like" suggestion, a new connection on social media, a product on a shopping site, a show on a streaming platform, that's a recommender system at work. These systems exist to solve one core problem. Out of a huge catalogue of items, which ones are actually relevant to this specific user? There are three main approaches worth understanding. The first is collaborative filtering, which works by looking at how users interact with items, not the item's content itself. It comes in two flavors: user-based collaborative filtering, which finds users similar to you and recommends what they liked, and item-based collaborative filtering, which looks at items similar to ones you've already liked. This is the backbone of a lot of streaming service recommendations. The second approach is content-based filtering, which flips the logic. Instead of looking at user behavior, it looks at the features of the items themselves. NLP techniques are often used here to extract meaningful features from text, like song titles or product descriptions, to find items with similar characteristics to what you've already engaged with. The third approach, matrix factorization, is more mathematical. Picture a giant matrix where rows are users, columns are items, and each cell represents some interaction, a rating, a purchase, a view. Matrix factorization breaks that huge matrix down into smaller matrices that capture underlying hidden characteristics. Think of them as latent taste dimensions that aren't directly labeled, but that the model discovers on its own. Techniques like singular value decomposition, or SVD, and alternating least squares, or ALS, are the standard tools for this. Matrix factorization shows up a lot in e-commerce, where it's used to recommend products based on purchase history. Building any of these systems starts with the same foundation as any ML project: collect and clean the data. Recommender systems are trained on large volumes of user data, preferences, interactions, context, and that data needs careful pre-processing before it's usable. From there, feature engineering matters a lot, and it depends heavily on which approach you're using. Collaborative filtering cares about user preference patterns, while content-based systems care about item attributes. Model training itself can be supervised or unsupervised, depending on the setup, using anything from k-nearest neighbors and support vector machines to full neural networks, with deep learning increasingly used to capture subtle patterns in user behavior that simpler models miss. Even with all of that, recommender systems run into some very persistent problems. The most famous is the cold start problem. What do you recommend to a brand new user, or for a brand new item, when there's no interaction history to learn from yet? Closely related is data sparsity. Most users only ever interact with a tiny fraction of the total catalog, which makes patterns harder to detect. Matrix factorization can actually make this worse, since it relies on relatively complete user item matrices to work well. And then there's overfitting. A model that gets too good at predicting one user's narrow past behavior can end up giving recommendations that don't generalize at all to new users or new items. Regularization techniques and careful tuning help, but this remains an active balancing act in the field. Closing remarks. So, across healthcare, NLP, autonomous vehicles, and recommender systems, a pattern shows up again and again. The same underlying ML pipeline: collect data, choose an architecture, train, evaluate, gets applied to wildly different problems. And each domain brings its own version of the same core tension: powerful results paired with real limitations around data quality, trust, privacy, and generalization. It's worth remembering that a lot of the core ideas behind ML, even artificial neural networks, go back to the mid-1900s. What's changed isn't the concept. It's that today's computers and today's flood of digital data have finally caught up to make those old ideas practical at scale. ML has come a long way, but as we've seen across every domain in this video, it's still far from a solved problem. The next stretch of progress isn't going to be about making models bigger for the sake of it. It's going to be about making them more secure, more reliable, and more robust. If you found this useful, let me know in the comments which application you want to see explored in more depth next, and subscribe for more machine learning breakdowns.